Hello, Mr. Collier here. Today we're going to talk about Chapter 5, Section 1, which is all about forces. My goals for this little discussion are to define forces, talk about how they're vectors, and describe how we measure forces. We're going to explain how they're created, and we're going to look at a few different types of forces, how they come to be, how they interact. So first, let's define a force. A force is anything that is a push or a pull, right? Something that has the ability to change the motion of an object, and that's going to be a big theme, this idea that a force can change motion. So that means that they can increase or decrease the speed of an object. They can take something that's already moving and change its direction. And really, ultimately, what that means is that forces can cause acceleration, right? Something we talked about in Chapter 4. There's lots of different ways to create forces. We're going to look at a few of them, but you already know some. You swing something, you create a force to make it move, like a baseball bat, right? Or throwing a ball. Other things can just kind of happen in other ways, like moving wind can create a force that moves a flag, or gravity, right? Just something that has mass is going to create forces, and we're going to talk about gravity as a force in Section 2. Ultimately, there are four fundamental forces. These kind of rule the way the universe works. We are going to focus on a couple of these. Gravity is going to be a big focus in this chapter, which is a force of attraction between all objects with mass. There's the weak and the strong nuclear forces, which we're not going to talk very much about in this course. And there's the electromagnetic force, which is that sort of idea that opposites attract, positive and negative charges. And we talked about that a little earlier in the year when we talked about chemistry. Force can be measured using a variety of units. You're probably already familiar with the pound, which is the English unit of force. There's 16 ounces in a pound. We use this to measure forces in the United States. So really, when you're measuring your weight in pounds, what you're measuring is the force that you are being pulled down with because of gravity. So it's the force that you're pushing down on the ground with. In the metric system, however, we use a force called a Newton, named after Isaac Newton, who we will talk more about in Chapter 6. And a Newton is pretty light. It's much lighter than a pound. If you have an iPhone, that's about what a Newton is. And really, how we define a Newton is that it's the amount of force it would take to make a 1 kilogram object accelerate at 1 meter per second. So, as I mentioned, the Newton is smaller than a pound, so we're going to need to do some conversions in this chapter. 4.448 newtons is equal to a pound. So, you can do some conversions, for example. If you have a 100-pound person, they would be 444.8 newtons. Forces are vectors, just like velocity and acceleration. It is a measurement that also includes a direction. If you push to the left or to the right, you have different effects, so we need to distinguish this. This is why force is a vector. Just like our other vectors, typically we're going to use positive to mean to the right and negative to mean to the left. We're also going to get some practice drawing vectors, where you will use an arrow to indicate the force, and the relative size of the force tells you the relative size of the arrow you should draw, and the direction of the force is the direction of the arrow you should draw. And we'll get some practice with this throughout the chapter. You'll see me draw little diagrams where I'm drawing forces represented with arrows. There's lots of different ways that forces can make things accelerate. One way is through direct contact. For example, throwing a ball, kicking a ball, air hitting against a parachute like in this picture here. This is probably the easiest force interaction to wrap your mind around, because you can see the two objects interacting. There's also forces that do what we call at a distance action. For example, gravity, right? You don't actually have to be touching Earth to be pulled down by its gravity. And we're going to spend all of section 2 and 3, talking a little bit more about gravity. And so these are called fields. Okay. Here are some different forces that you can classify. We've got the tensional force, which would be a contact force. The air resistance here would be another contact force. And, of course, gravity is one of those field forces. And sorry, I skipped pushing a button. That's also a contact force. All right, the next thing I want to talk about is, since we're going to be talking about gravity a lot, it's important to distinguish between the terms weight and mass, because we're going to be looking at each of them in great detail throughout this whole physics section. So mass is a fundamental property of matter. It's how much matter something is made of, and we measure it in kilograms. Weight, however, is a force, and we measure it in newtons. Weight is this thing that depends on your mass, but also how much gravity. So, for example, here on Earth, there's 9.8 newtons of force acting on every kilogram of mass. That's just the strength of Earth's gravity. And it can change a little bit depending on where you are on Earth, how high you are off the surface, but generally 9.8 is the accepted value. So something with more mass also has more weight. However, if you went to the moon, while the mass remains the same, right? This is a 10 kilogram rock. This is a 10 kilogram rock. On the moon, which has less mass, there is less gravity, and so there is going to be less weight. And we'll do some calculations with that as the chapter goes on. The way that you calculate weight is that it is mass times gravity. It's pretty simple. So mass, we've talked about, is measured in kilograms. Gravity is going to be measured in either newtons per kilogram, like you see here, or you might also see it as meters per second squared, which is that acceleration unit. Weight is going to be abbreviated with this capital F, little w, the force of weight. So if you have any two of these, you can calculate the third. So for example, you can be asked to solve for weight, asked to solve for mass, or asked to solve for the gravity on a particular place. And here is the way that those equations rearrange to solve for each of them. And this little chart is using W for weight. As I mentioned, I'll usually use FW. So, for example, if you want to calculate the weight of a 60-gram person on Earth and on Mars, you're going to need to know the gravity on both of those places, and you know the mass, and that'll let you calculate their weight. So, the mass is 60 in both scenarios. Gravity on Mars is 3.7 newtons per kilogram, and on Earth, as I mentioned, it's 9.8. That's a number that's going to come up a lot. So, 60 kilograms times 9.8 newtons per kilogram. On Earth, you weigh 588, and on Mars, you weigh 222. Please note that you weigh less on Mars because gravity is less, but your mass is the same no matter where you are in the universe. Also, we've been talking about significant figures a lot this year. Here is a problem where they only gave you one significant figure in that number 60, and so we needed to round our answers off to one significant figure. Here are some links. I'm not going to go through them right now, but if you want to check them out sometime, they will let you look at what your weight is at other places in the universe. It's kind of interesting. There are some planets and moons where it's similar to Earth and some where it's a lot lighter or a lot heavier. We're actually going to skip talking about tension right now, which I think brings us to the end of this lecture. Thanks for listening, and I hope you understand a lot more about forces now.